Okay. So this is going to be a quick video, as quick as I can possibly make it. So a lot of people believe in the idea that the collapse of a wave function in a double slit experiment like this one, or in other experiments where you have wave-particle duality, is caused by the interaction of the measuring devices with the particle that's being tested. So what I'm about to show you will refute that. So what I'm about to show you is called interaction-free measurement. So we are actually able to make the measurement without interacting with the particle in any way. So this here is what shoots the particle. In most cases, people like to think that that is going to be shooting electrons or photons, subatomic particles, and they like to use this as some kind of evidence for the claim that quantum mechanics and wave-particle duality is only relevant for subatomic levels of particles. Well, I'm going to link to you a paper which shows that they have used 800 atom large molecules. So 800 atoms large, that's going to be 5,000 protons, 5,000 neutrons, and 5,000 electrons. So we're going to call these single objects that this thing shoots out through the double slit experiment as 800 atoms large molecules. So when we run this experiment with no detector in either one of these slits here, what we're going to get in the back slide is a wave pattern. So that's the pattern that shows that this single object is actually not a single object, but a wave of potentials that is going through both of these slits, and all of the potential possibilities interact with each other and create a wave pattern in the back, even though we're sending them through one at a time. So this single object, it's not actually a single object when it's unobserved. It's a wave of probability that can interact with itself and produce a wave pattern in the back. So what happens is, of course, when we measure, which is to say, when we know which path it takes, when it goes through this slit or this slit, then it no longer goes through both of the slits. It then chooses either one of the two slits and behaves just like a single object would, and creates a different pattern in the backslide, which would be just two bands in the back. Instead of a wave pattern, it's a particle pattern, just two solid bands right behind the two slits, indicating that it traveled through just one slit at a time, like it's supposed to, like a materialist universe or an objective reality universe would predict that it should. So the argument, of course, is that if you place a measuring device on both of these slits, and we know either it goes through slit A or slit B, then we get this single band pattern, particle pattern in the back with just two bands. That what causes that collapse from the wave to the single particle is the fact that those measuring devices must necessarily, in order to detect which slit it's going through, interact with this particle, and that interaction causes the decoherence, and it collapses the wave function and creates the particle pattern in the back. So the way that is refuted is to do this. So every time we run this experiment with no measuring devices here, we get a wave pattern in the back, indicating that it went through both and we got a wave function. Now if we place measuring device M1, so that's measuring device 1 on just slit B here. Okay, so let's say we have a little monitor here, which tells us if something's detected or not on slit B. So let's assume we're running this experiment over and over. Every time we run it, we just send one of these 800 atoms large molecules through the experiment. So let's say we send one through, and let's see, it goes through here, and it just hits this slide and bounces off. Okay, so we got no detection here, and we got nothing that happened back here. So let's say we run it again, it goes through, and it goes through slit B, and then bing, we get a detection on our slit B saying that yes, we detected an object went through slit B, and then we're going to get a detection in the back here. It's going to be in slit B right here, right in this range right here. It's going to not right there because it has to consistently go through this slit as a single object. It has to hit right there. So that would correlate every single time we run the experiment. So now let's say we removed this measuring device completely out of the equation again, and we ran this experiment. Then we would see that it's actually going through as a wave, and two waves interact with each other, and then when we run the experiment one time, we get a dot over here. When we run it again, we get a dot over here. When we run it again, we get a dot way over there. When we run it again, we get a dot way over here, and eventually it turns into this long bunch of bands wave pattern in the back. So that's never going to happen when we have our measuring device M1 on slit B here. We're always going to get dots here or here, never in any of these other spots, here or here. So if we do have our measuring device on slit B, I wonder if you can see where I'm going with this yet. So it's detecting slit B, and we run our experiment, and let's say it goes, and let's say it goes through slit A this time. And it goes through slit A, and boop, it lands right there, right behind slit A where we would expect it to. What happened there? So what happened there was that the object passed through slit A and never interacted with our measuring device. We never got a detection. So the object goes through slit A, and we do not get any detection whatsoever right here. We don't get half a detection, some of a detection. No detection at all occurs on our M1 measuring device for slit B because it went through slit A, and it hits the back device as a collapsed wave function. As it hits the backslide as a particle with the particle pattern, meaning the wave function did collapse. So what this shows effectively is that the wave function collapse is not caused by interaction between the measuring device and the particle, because sometimes it goes through this slit and it is not interacted with at all with our measuring device, and yet the wave function is collapsed. What this shows instead is that decoherence does not occur because of interaction with the particle. The wave function collapses because we know which path it took. Because even though this measuring device never interacted with the particle, we know, because we got a zero result here, that it must have gone through slit A to have arrived here. It could not have gone through as a wave. It could not have gone through slit B because we didn't get a detection. So we know for a fact it went through right there. And if we know that it went through right there, then it must have gone through as a single particle. It could not be a wave. And so that is why the wave function collapsed, because of it's a logical coherence. If we have the which path information, if the which path information is available, the wave function collapses. Not necessarily caused by interaction. And so this experiment, of course, as I'm showing you here, is a watered down version of the actual experiment, but as with most of these important experiments, Anton Zeilinger actually performed this exact experiment and proved that it was possible in 1994. So I'm going to link the peer-reviewed paper describing that actual experiment in the description below. Thank you.